This video is on finite differences, and it's a part of lesson 3.1, exploring polynomial functions. The idea behind a finite difference is that, as you saw in grade 9 or grade 10, you could find differences in y values as the x stays constant. So here we have a table of x values with related y values, and if you notice, the x's are all going up by 1. We've explored in grade 9 and grade 10 what relationship happens when we find the first difference. If the first difference comes out constant, we know, or we can conclude, that we have a table of values that represents a line. If the second difference comes out constant, we know that we have a relationship that represents as a parabola. It's further true. It's also true that as we increase the degree and we continue to look at polynomial functions, that the third differences would represent a degree 3 polynomial. A fourth difference, if they're constant, would represent a degree 4 polynomial, and so on and so forth, up to whichever degree you choose to go to. So basically, you can keep calculating differences until you find one that's constant. And if you can't find one that's constant, you can conclude that the polynomial function, or that it's not a polynomial function. And you wouldn't keep finding differences. Like, you wouldn't go to like the 100th difference looking to see if it's a polynomial degree 100. Reasonably in this course, we'll look up functions up to degree 6. And when we're doing a question like this, you could expect it's probably a degree 3 or degree 4, but not much higher than that, because that'd be ridiculous to keep finding differences, because it does take a little bit of work. What else is significant about those differences is that once you find that difference that's constant, that number represents something. It represents a few things. First, if it's constant, it tells you which degree the function is. For example, if the fourth difference is constant, then we'd have a degree 4 polynomial. But that number, whatever number it ends up as, whatever that constant number is that's consistent as your fourth difference, it also will have the same sign as the leading coefficient in the polynomial function. The leading coefficient is the number in front of the term with the highest exponent. So if it's a degree 4 polynomial, it's the number in front of the x to the exponent 4 term. Also, that number is equivalent to a times n factorial, where a is the leading coefficient and n is the degree. And I'll show you that relationship in a second. So here we go. We have a table of values. If we look for the first differences, we can see if this is a degree 1 polynomial. So when you're looking for a difference, you're asking what's changing or what's happening to negative y to make it negative 12. And in this case, we're increasing its value by 24. And if you're not sure how to get that number, you take the second value and subtract the first value. So negative 12 subtract negative 36 is 24. And you can keep going. Negative 2 subtract negative 12 is 10. 0 subtract negative 2 is 2. 0 subtract 0 is 0. 4 subtract 0 is 4. And 18 subtract 4 is 14. So what you can see here is that, well, the first differences aren't constant, so we don't have a linear relationship. But we can keep going. We could find the second difference. And here we're decreasing by 14, so 10 minus 24 is negative 14. Again, decreasing, this time by 8, decreasing again by 2, increasing by 4, and increasing by 10. So the second differences aren't constant, so we don't have a degree 2 polynomial, we don't have a quadratic, we don't have a parabola. Third, what's happening? Well, we're going up 6, because negative 8 minus negative 14 is 6. Again, it's up 6. Negative 2 minus negative 8 is 6. 4 subtract negative 2 is 6 again, and 10 subtract 4 is 6. So here we have a constant third difference. Therefore, what we can conclude is this is a degree 3 polynomial, which means that polynomial is going to have an x cubed term in its equation. And you can actually get even more specific. You can find out what that value is in front of x cubed. Is it 2x cubed? Is it negative 4x cubed? And you can do that by using the relationship described here. The nth differences are equal to a times n factorial. So what that means is that this difference, the third difference, the number 6, because that was your constant number, 6 is equal to a times n factorial. What's a? A is the leading coefficient, so a is the term in front of the x cubed, and n is the degree. We just found out that this is a degree 3 polynomial. So this relationship says 6 is equal to a times 3 factorial. And that exclamation mark, the people who are in data right now may know that actually you will know because you've done it, that exclamation mark is factorial. And it means that you take the number and multiply it by each whole number less than it to the number 1. So what would that look like for 3 factorial? Well, it would be 3 times 2 times 1. We don't multiply by 0 because that would make everything 0. We don't use decimals, it's just the whole numbers. 3 times 2 times 1 is 6. So we have 6a equals 6, which means that a must equal 1. What's a again? A is the leading coefficient. So this means the first term in this polynomial is 1, and it's a degree 3, so x cubed, or just x cubed. If that a value came out as 4, this would be 4x cubed. If it came out as negative 2, it would be negative 2x cubed. So that's how you can use finite differences to determine the degree and the leading coefficient in a polynomial expression or equation. Thanks for watching.